Hello everyone, welcome to the lecture again. In the last class, we solved some example based on the principle of virtual work. Today, we are going to continue the discussion and we will solve some more example based on the same concept. So, before I write down the problem statement, let me just summarize what is the principle of virtual work. Suppose I have a rigid body and on this rigid body there are various external forces are acting. Okay. So, let us say P is one such force, Q is another force and let us say there is some moment that is also acting on the rigid body. Let us say corresponding to this force P, if the virtual displacement is delta x, corresponding to this force Q, there is a virtual displacement, let us say delta y, and because of the moment, let us say the virtual displacement is delta theta, then sum of them has to be equal to 0. Now, after that there is one more step, you have to write down this delta x, delta y and delta theta in terms of the generalized coordinate. So, you have to identify which one is the generalized coordinate, you write down this equation in terms of that and we solve it to find out whatever is the unknown or whatever is the relation between them. Now, let me write down the first problem statement. And the problem statement is following: determine the torque M on the activating lever of the dump truck necessary to balance the load of mass M with center of mass at G when the dump angle is theta. So, first let me make the free body diagram of this. So, let us say this is my x axis and we have this dump. This is making an angle theta with the horizontal because it is given that this angle is theta. And this length is B. So, its center of mass is at Z and this length is B, this height is A and its mass is going to act downward. So, let us say it is mg and over here a moment M is applied and this is kept into the equilibrium by this assembly. This point is given as D and this is the free body diagram. You can see here that the generalized coordinate is theta because with this theta I can identify the location of all part of this system. Now, let us follow the sign convention. So, you can see here that the force mg is acting downward. So, let me take this as positive y, this is in the same direction in which the force is acting and the moment is acting in that direction. So, let me take positive m in that direction. So, now we have the sign convention. Let us say this height is y and this y I can write down in terms of a's and b's. So, you can see here that this y is nothing but y1 plus y2 and from the geometry you can see that it will be a cos theta plus b sin theta. Now, let us write down the principle of virtual work equation. So, we have delta u equal to 0. So, we have force mg. So, let us say mg delta y plus m delta theta equal to 0. Now what we have to do is, we have, so as I said, here the generalized coordinate is theta, therefore this delta y I have to write down in terms of delta theta, but I know this relation, so therefore I can find out what is delta y. So from here my delta y will be minus a sin theta plus b cos theta delta theta. Let us put in equation number 1. So we have minus mg a sin theta minus b cos theta delta theta plus m delta theta equal to 0. Therefore, m comes out to be mg a sin theta minus b cos theta. So here in this example I have not shown you the virtual displacement, how the virtual displacement will happen, but of course I mean you can identify, because of the force mg this dump is going to come down, this is one virtual displacement, and because of that your delta y is going to change, and because of the moment m you can assume that the virtual displacement will be like this, and your theta in that case is going to increase. But since we have solved many problems, so we can think of it and we do not need to now show it here. Now let us look at one more problem statement, and the statement is following: the portable car hoist is operated by the hydraulic cylinder which controls the horizontal movement of end A of the link in the horizontal slot. Determine the compression C in the piston rod of the cylinder to support the load P at a height h. So, let me first make the free body diagram of this. At A, because of the piston, there will be a horizontal force. So, since it is a cylinder, let me call this force as C, and we have the force P acting at this point, and then various geometrical parameters are given. So, for example, this is B, this is B, and this is also B. This height is h. Let us say this distance is x. Now, you can see that the force is acting in that direction. So, therefore, let me take plus x like this, and the force P is acting downwards. So, let me take plus y in that direction. So, I can write down the principle of virtual work equation. It is delta u equal to 0. So, which is P delta h plus C delta x equal to 0. Now, let us identify what is the generalized coordinate in this system. So, if I define my theta here, then with this theta I can identify where the members of this systems are. So, therefore, this theta becomes the generalized coordinate. Now, given the fact that this is B, this is B, this will also be theta. So, therefore, since theta is the natural choice and it is the generalized coordinate, therefore, we have to write down this delta h and delta x in terms of theta. So, let us see how the h and thetas are related. So, you can see from the geometry that h will be 2b sin theta and x will be 2b cos theta. Therefore, delta h will be 2b cos theta delta theta and delta x will be minus 2b sin theta delta theta. Let us put this in equation number 1. So, we have p 2b cos theta delta theta plus c into delta x is minus 2b sin theta delta theta equal to 0, or we get p cos theta equal to c sin theta. Therefore, p is nothing but p cot theta. However, this theta was not mentioned in the question. So, therefore, let us eliminate this theta in terms of the given parameter that we have a, b's and h. So, cot theta is nothing but x over h and x is square root 4b square minus h square over h. Therefore, c will be p square root 2b over h whole square minus 1. So, in equilibrium the force C and P should be related by this relation. Now, let us look at another problem statement. This question is based on a spring. The problem statement is following: if the spring has a stiffness K and an unstretched length L naught, determine the force P when the mechanism is in the position shown. Neglect the weight of the members. So, to solve this question, let us first make the free body diagram. So, we have a force P acting at point B. From here we have members of length L and they are connected by a spring of spring constant K. This angle is given as theta and here you have a pin support and here you have a roller support. This point is C, this point is A and that point was B. The spring constant is K. Now, since the force P is acting in that direction, so let me take this as positive x and in this direction let me take positive y. Now, let us say this length is x and this height is y. So, you can see here that the force P is balanced by the force which is provided by the spring and therefore, the system is in equilibrium. So, there are two forces P and let us say the spring force is F. So, we have equation delta U equal to 0 and force P into delta x plus spring force F into delta y is equal to 0. Here you can also appreciate that theta is the generalized coordinate. Therefore, this delta x and delta y I have to write down in terms of theta. Okay. And also note that delta y here is the virtual displacement. So, I would like to explicitly mention here that this delta y is the virtual displacement. Delta x is also virtual displacement in the x direction, delta y is the virtual displacement in the y direction. Now, let us write down this delta x delta y in terms of theta. So, from the geometry you can see that x is L sin theta and y, the way we have defined, it will be 2L cos theta. Therefore, delta x is L cos theta delta theta and delta y is minus 2L sin theta delta theta. Now, in the question statement P is mentioned. So, therefore, P is given. So, the spring force is not given. So, let us write down what is the spring force here. So, F equal to K times delta y, where this delta y, you know, it is the stretch in the spring. Okay. So, we have to find out how much the spring has stretch in this particular case. It is given that the unstretched length of the spring is L naught. So, therefore, delta y will be y minus L naught. Okay. So, therefore, again this delta y I can write down in terms of generalized coordinate because y is known. So, therefore, this will be 2L cos theta minus L naught. Now, we are ready to rewrite equation number 1 in terms of the generalized coordinate. So, let us put everything in equation number 1. So, we have P times delta x is L cos theta delta theta plus F is K times delta y. So, K times delta y is 2L cos theta minus L naught into delta y. Delta y is minus 2L sin theta delta theta and this will be equal to 0. So, from here delta theta can get cancelled, L can also get cancelled and we have P equal to K times 2L cos theta minus L naught tan theta. This is the relation between P and K for the system to be in equilibrium at angle theta. Now, let us look at one more problem statement and the problem statement is following. The spring of spring constant K is unstretched when theta is equal to 0 degree. Derive an expression for the force P required to deflect the system to an angle theta and it is given that the mass of the bar is negligible. So, again let us first make the free body diagram. So, at A we have a roller which is connected by a spring of spring constant K, and then we have the bars, this length is L, it is given that this angle is theta, and here the force P is acting to keep everything in equilibrium. This point is given as C and this point is given as B. Let me show you the virtual displacement because of P, but we know like how it is going to look like. It is not required now, but anyway let me just show it. So, let us say this length is x, then the virtual displacement will be dx, and because of the spring the whole system is will try to go up. So, therefore, that will be the other way around, something like that. Let us say this length is y, and therefore, let me take this direction as positive x and this direction as positive y. Now, I can write down the equation for the virtual work. So, this is delta u equal to 0. We have force P acting in the x direction. So, virtual displacement is delta x, which is consistent with the constraint that we have, plus F delta y equal to 0. Now, as usual we have to identify what is the generalized coordinate, and from here it is obvious that theta is the generalized coordinate. Therefore, this delta x and delta y we have to write down in terms of theta. So, for that let us look at the relation between x and theta. So, we have x equal to, from the geometry it will be L sin theta and y will be 2L cos theta. Therefore, delta x will be L cos theta delta theta and delta y will be minus 2L sin theta delta theta. Let us find out this force F. So, as we have done in the previous case, F will be k times delta y, where this delta y is the stretch in the spring. Okay. And delta y will be 2L minus y, because it is given that the spring is unstretched when theta is equal to 0. So, in that case my y will be 2L. So, when the spring is unstretched, therefore, in this particular case it will be 2L minus y. Therefore, delta y I can write down. So, we have this y in terms of generalized coordinate, it will be 2L minus 2L cos theta. Now, we can put everything in equation number 1. So, let us put in 1. So, we have P times delta x is L cos theta d theta, L cos theta delta theta, plus F we have calculated, F is k times delta y. So, k times delta y is 2L minus 2L cos theta into small delta y, okay, and this delta y is minus 2L sin theta d theta equal to 0. So, from here we can see that P L cos theta equal to 4 L square k 1 minus cos theta sin theta, L will get cancelled and cos theta we can take it on the right hand side. We will get P equal to 4 k L tan theta minus sin theta. With this, let me stop here. See you in the next class. Thank you.